Okay, so let's look at this relative strength of acid problem and do an example here. So in this equation, we have acid and a base going on one side, another different acid on the other side. So we can look at whether the reaction is favored toward this direction, toward the right or the left, depending on which acid is stronger. Will the reaction ride to the right or the left? So if this acid is stronger, then it should drive the reaction this way. If this is the acid on the other side, if it's stronger, then you would expect to drive the reaction the other way. So we can take a look at that. So we can consider the K for the overall reaction, again, just products over reactants here. And we can also consider the reaction for just each acid alone in water. So we can consider it separately as well. So first, we can take a look at one acid. So if we take a look at this acid alone in water, it will form H3O plus and NH3 minus. So when it gives up its hydrogen ion to the water, and then it forms its conjugate over here. So now are we going to look at a Ka or a Kb? Ka. And so we're going to have our products over our reactants, and the number is quite large, 20, for that Ka. And now we can look at the other reaction as well. So we can look at this acid in water here and form your hydronium ion concentrations and your conjugates. Again, we're looking at that acid in water, so it's a Ka. And we have our products over our reactants. Now we have a number of 5.6 times 10 to the minus 10. So we can add those, or we can consider those two equations back together. And this time we're going to be subtracting the equations from each other to get our sum equation. And because we are subtracting, we're going to end up dividing the equilibrium constants. So when we add the equilibrium constants together, we multiply things. And if we're subtracting, we divide. So the K in this case is going to be equal to the Ka of the first acid over the second acid. And you can prove this to yourself. You write up the Ka here and the Ka here. And then some of your terms, the hydronium ions cancel. And you get the K overall equilibrium constant that we wrote in the beginning. Again, products over reactants. We know the value for Ka for one acid. We know the value of Ka for the other acid. And we can divide those to get the K for the overall reaction. And then you can tell me what that K means in terms of which is the stronger acid of the two. And which side of the equation does the reaction lie to, the right or the left? All right, let's give 10 more seconds. Yeah, people did pretty well on this. So you could have thought about it in terms of the overall K or of the individual Kas. So the stronger acid is the one with the larger number, and HNO3 had a number of 20, so that was pretty big. So that's a really strong acid. And because it's a strong acid, it'll lie to the right, so it's going to push toward products. A strong acid, so it wants to dissociate a lot, so it would push it that direction. And you can see that also in terms of the equilibrium. Overall equilibrium constant, if we go back to the slides for a minute. So this number of overall K is also quite large, very large. So that means a lot more products than reactants at equilibrium. So again, those are what you can determine. If you're given a table of Ka values, which on the test you will get a table of Ka values, you can tell me a lot about different reactions knowing that information about Kas.